In this video, we'll be learning how to graph simple rational functions. So before we begin actually graphing rational functions, we want to make sure that we know what a rational function is. And a rational function is any function that has the form f of x equals p of x over q of x, where p of x and q of x are polynomials and q of x does not simply equal 0. So essentially what this is saying in simpler, less math-sounding terms is that a rational function can essentially range from something that looks like, f of x equals 4 over x. So something very, very simple where, p of x would equal the 4 and q of x would equal the x, to something even more complicated like g of x equals x squared plus 4x minus 6 over 3x squared minus 7. So rational functions are going to range from something that looks quite simple here, where it is essentially a fraction made up of two very simple functions, to something that is even more complicated. Now in this video, we're going to focus on these simple functions. How do we graph these very, very simple rational functions and put them onto the coordinate plane? Now to begin, let's start off by looking at the simplest of the rational functions, which is f of x equals 1 over x. So this is pretty much as simple as these rational functions get. Now the shape that this graph is going to make, that we'll see in a second, is called a hyperbola. And essentially what's going to happen is, because of the shape of this particular function, it's going to have two symmetrical branches, and you'll see where they appear. And it's also going to have two asymptotes, one that is vertical and one that is horizontal. And you're going to see that they're both going to happen at 0 themselves. So let's start off here just by making a table of values so we can see what's going to happen with this particular function. So I'm going to start off looking at, let's say, values like 4, 3, 2, and 1. So if I start putting values like 4, 3, 2, or 1 in there, what I see is that when I have x is 4, I have y is 1/4. When x is 3, y is 1/3. X is 2, y is 1/2. So if I were to plot these, they're pretty small down here, getting very, very close to that x-axis, but not quite crossing it. So you can see they're getting a little bit higher, but they start off pretty low. Then when x is 1, y is simply 1. And then from here, if I do x is 0, I end up with 1 over 0, which is something that doesn't work. So what I'm going to do here is, instead of doing 0, because I can see that something weird is happening at 0 and x can't ever equal 0, instead I'm going to look at an x value that's just, between 1 and 0. So say we do something like x is 1/2. Well, when I put x's 1/2 into here, I get 1 over 2, which then if I use keep, switch, flip, basically turning it into it's multiplying by the reciprocal, this becomes 1. So when x is 1/2, y is 2. So essentially what I learned here is that x cannot equal 0, so it can't cross this line, which means there's an asymptote there, and essentially it's getting really, really close here but not crossing, and then getting really, really close here but not crossing. So we've got a vertical asymptote here. You can see that it can't become x is equal to 0. And then we have a graph that is centered only in that first quadrant. So now if I start to find additional points here, so let's say that I focus on -1, -2, -3, and -4. So if I focus on those, I end up with -1, -1/2, -1/3, and -1/4. So basically I notice it's the same pattern as up here, but it's just occurring in the quadrant that has all negative numbers. So I would have -1/1, 2 -1/2, the 1/3, and the -1/4. So I can see it's getting really, really close to the x-axis there. And then if I kind of do the same thing, I can see just if I use x as -1/2, I can see that if I put that over 1 and then I multiply by the reciprocal, I end up with -2. So it's going to shoot downwards here and get very, very close to this y-axis. So I can see here that I have this graph that has two symmetrical branches. You can see that it has this piece in quadrant 1 and this piece in quadrant 2. They are symmetrical. You can see that they're the exact same looking thing. And then we have two asymptotes. We have a vertical asymptote at 0, and we have a horizontal asymptote at 0 as well. So we have a horizontal asymptote and a vertical asymptote here at y equals 0 and x equals 0. Now, our domain and range are pretty much all real numbers, except for in these cases, we can't have x or y equals 0. We can see that because they have asymptotes that they never cross. But we're using all of the positive x values up here in quadrant 1, all of the negative x values down here in quadrant 2, and then the same thing with the y values. Positive y values up here, negative y values up here. So what we can do is we can say that the domain is all real numbers. If you want a fancy way of representing that, it's the double-lined R. So this means all real numbers. But the difference is it's all real numbers, but x cannot equal 0. And then here the range is the same thing. All real numbers, y cannot equal 0. So it's basically acknowledging that x and y can be everything, except for x cannot be 0 and y cannot be 0. So now let's practice graphing some of these rational functions with an a value. So notice that all I'm doing here is I'm changing the number that is up in the top of the fraction to something that is a number other than 1. So here we have a number that is 2. So what I'm going to do here is I'm going to make a table of values, and I'm going to start with, the same 4, 3, 2, 1. I'm going to skip 0 because I know that the denominator can't be 0, so I know that x equals 0 will not work. Then I'm going to look at -1, -2, -3, and -4. So because I know that the denominator can't be 0, I know that there's a asymptote here, and then we have our asymptote here. So just based on the parent function, we know that our asymptotes, we're going to have a vertical asymptote at 0 and a horizontal asymptote at 0. So now if I find some coordinate points, I have 2 over 4, which is 1/2, 2 over 3, 2 over 2, which is 1, and 2 over 1, which is 2. So if I plot these out, I have 1/2, 2/3, 1, and 2. So I can see how it starts. It's a little bit different. The points aren't identical, but it has that same general shape. And then if I complete the points down below, I have 2 over -1, which is -2, 2 over -2, which is -1, 2 over -3, which is -2/3, and 2 over -4, which is -1/2. So I have this same pattern happening down here, so I can create my graph. Now I end by finding my domain and range, and because of where my asymptotes are placed, my domain and range are both all real numbers, but x cannot equal 0, and all real numbers, but y cannot equal 0. So let's do one more example here with an a value that is negative to see how that might impact the graph. So here we're going to start with our table of values. So I'm going to do again 4, 3, 2, 1, and then -1, -2, -3, and -4 to get the other side of that graph. Skipping 0 because I can see that x equals 0 is going to be a problem with the fact that there's a 0 in the denominator. Now because of the parent function having a horizontal asymptote here, I know that the horizontal asymptote is still going to be with a vertical one at 0 and a horizontal one at 0. So those are imaginary lines that my graph cannot cross. So now if I start plugging my points in, -4 over 4 is -1. Then I have -4/3. -4 over 2 is -2. -4 over 1 is -4. So if I go to my graph, I have x is 4, y is -1. And then x is 3, it's a little bit more negative, then we're at 2, then we're at 4, so I can see that same general hyperbola shape here. And then if I use my other negative x coordinates, I notice that I have negative 4 over negative 1, which is a positive 4, negative 4 over negative 2, which is a positive 2, negative 4 over negative 3, which is a positive 4/3, and negative 4 over negative 4, which is a positive 1. So if we do x is negative 4, y is positive 1, then we have this one a little higher, this one at 2, and this one at 4. I can also see that same general hyperbola shape. So that negative actually causes a reflection over the axis there, and we can see that we end up in quadrant 2, and we end up down here in quadrant 4. Now, the nice thing is that the domain and range don't actually change. The domain is still all real numbers except for x equals 0, and the range is still all real numbers except for y cannot equal 0 because we can't cross those asymptote lines.